Okay, hello everyone. I am so honored to introduce you to Professor Jürgen Kurz, who will be speaking for us today. Professor Kurz is a professor of nonlinear dynamics at Humboldt University in Berlin. He's also a senior advisor at the Potsdam Institute for Climate Impact Research. Before that, he was a professor at University of Potsdam and the Max Planck Society. He is internationally recognized for his research on complex synchronization phenomena, complex networks, time series analysis and their applications in climatology, sustainability research, and physiology and engineering. He has been awarded the Richardson Medal of the EGU, the Alexander von Humboldt Research Award, and the Longrange Prize. And he also holds several honorary doctorates and honorary professorships. So with that, I will allow Dr. Kurz to take it away.
Okay, thank you very much. Make this little change here. Okay, yeah, thank you very much, Jackie, for the very kind words and the introduction, and for the invitation, of course, to explain a bit what we are doing. Especially on climate and a better understanding of extreme climate events from complex system science. Now it's not working. Why? Now it's working. Good. One motto of my talk is: are modern concepts of complex system science useful for Earth science? Usually I had to convince people, but now it's much easier for me, because last year 3 people from this direction got the Nobel Prize, Klaus Hasselmann, Giorgio Parisi, and Syukuro Manabe. And the description of their award was for their work on describing complex physical systems, also what we call complex system science, including foundational research that created a pioneering mathematical model of Earth's climate and predicting that increasing levels of carbon dioxide in Earth's atmosphere would raise global temperatures. What does it mean in speciality? Let me give only 2 highlights of what Hasselmann and Manabe did. Hasselmann already introduced in 1976, also almost 50 years ago, you should not forget, 50 years ago, a stochastic climate model. This was that time revolutionary. He designed a coupled ocean atmosphere cryosphere land system, as a very combined model. And the clue in this model was that he considered the climate system as a slowly responding part of the whole system, and the weather, the shorter timescale thing, as a stochastic component. And this way, he could write down a Fokker-Planck equation, where you have, of course, propagation term and diffusion term, depending on climate state Y here. And what was very important of this approach was the finding, or the result, that the distribution for a stationary climate, he could show that predictability is limited. Of course, we knew this already from Lorentz, from the 63 paper, but this was for a very idealized fluid dynamics model. Here we had for the first time a very realistic climate model, and he could really show that predictability is limited due to the intrinsic properties of the system. And what is also interesting, that the third in this round of the 3, Giorgio Parisi, mentioned in his paper on stochastic resonance that he was inspired by this work by Klaus Hasselmann in order to go and find this stochastic resonance, and he could explain also glacial dynamics and long-term dynamics. This is another one by Manabe. He also had such coupled models, And a specialty was that he also included the CO2 concentration in his ocean atmosphere model. This was in 1980, the first paper on this, the first basic paper on this. And he considered then the icing. That means considered both poles. You see here, this is Antarctica, Arctica, over the year. This is from January till January. And if you have here some colors, as darker, as more icing it is, but then it's ice. Here in the middle, of course, no ice. And when he included the CO2 contents as it was in 1980, he found such a seasonality in the Arctic ice sink and almost constant in the Antarctic. But then he played, this was all on computer and with brain, there's a lot of brain, of course. And then he found the following when he included 4 times CO2. That increase of CO2 is enormous. And he found then a very much stronger variability of icing in the Arctic. And you see almost no ice in summer, in the summer months. And even in the Antarctic, you have a much less icing. And this was his prediction without data that time. And this is what was found, almost exactly found these days. That means he really predicted with his models such type of CO2 impact on climate. And this is, I think, really genius. You cannot do more. You have a model, you have a new technique, and then you make predictions, theoretical predictions, which become reality, unfortunately become reality several decades afterwards. But you know that climate and climate change is close to politics, especially the risk analysis and risk discussion. One important field of politics is a United Nations Climate Change Conference of the parties called COP, which was starting in Berlin in '95. And we had in this year in Egypt, the 27th such conference, and there were ups and downs in these conferences. One highlight, of course, was in 2015, the so-called Paris Agreement, that we should not become an increase of climate increase of over 1.5 degrees. That time all countries agreed, also US with Obama, President Obama. But you see, all this is dynamic, is fragile, if you wish, such agreements, because a little later, the US President Trump say no and quit this agreement. But as far as I know, US is now in again. But also this year, it was accepted that there is climate change and so, and there is now some fund for loss and damages. But in all the documents, oil and gas are not included as impact materials, and of course due to strong forces behind the scenery, and there you see that all is not satisfactory, let me say, to be. But I will not talk more about politics, more about science, approaches and perspectives. And to start with, let me remind you a bit about basic physics coming to the climate. One was more than 100 years ago by Svante Arrhenius. He found already that greenhouse gases can indeed induce a temperature increase. Then a little later, Wilhelm Bjerknes was the first to use physics for weather prediction. Also not only statistics and empirics, but also physical equations, Navier-Stokes equations, etc. And this process found a highlight in the book by Louis Frey Richardson on weather prediction by numerical process 100 years ago, where he described how one should go ahead with this way. It's really fantastic. But this book, all these results were too early. There were no computers available, and it needed about 3 decades till genius as John von Neumann also and others used the computers to bringing this idea into practice and to really construct weather prediction based on numerics and computers. But nevertheless, basic mechanisms are unclear, especially for prediction, and therefore there's a lot of challenges to solve. But let's look to the system Earth as a whole. As is shown here, you see there are many ingredients: biosphere, cryosphere, atmosphere, a lot of processes, and a lot of interactions, positive and negative feedbacks. And therefore, some people call such a scheme of interaction a horrendogram. But one can make it a bit simpler. I like more such simpler things here. The main ingredients are shown: cryosphere, ocean, atmosphere, land and surface, of course, and in the middle are we, and with all our positive and negative actions. And you see there are really a lot of feedbacks, and this is what one has to model to understand this system Earth as a whole, which is a huge challenge, and I will tackle only a few sub-problems of this. But let me mention that this Earth is a highly complex and dynamic system. Let's look, for instance, to the temperature, the global temperature during the last 100,000 years. And you see we have here is never constant, and here was a strong jump. What was the reason? The reason was a Toba eruption on Sumatra, one of the largest volcano eruptions in the last several thousand years, which induced a strong increase of temperature. But then the system Earth came back, but never became quiet. Here are a lot of variations, so-called Dunsgrad-Oeschger events, but only during the last 10, 12,000 years, we are in the Holocene, which is almost constant in temperature. And one can say we started from glacial chaos to the climate paradise. But let's look a bit later into the paradise. Is it really a paradise or not? And what about the future of this paradise? What are the climate changes as the long-term factors? One is the celestial mechanics, as the motion in our solar system with precession, obliquity, and eccentricity. And this leads then to the so-called Milankovitch cycles, which were found by Milankovitch in 1941. And this is one, which are 100,000 years, 40,000 years, up to 200,000 years, the cycle lengths. And the other rather long-term is the greenhouse effect, as found by Svante Arrhenius, as I mentioned already, in 1896. But what are we doing as anthropogenic influences? And one is, of course, the CO2 concentration. This is shown here for the last several thousand years. And you see it's almost constant. And in the last few years, last decades, we have this strong increase, which is going on. It is not stopped, as you all know, it's going on. And then there's a debate, what is the impact of this CO2 concentration? And if you look at the same time for the temperature, global temperature reconstructed from several data sources, you see it looks very similar, almost constant. This is here a rather small scale. And then during the last decades, an abrupt increase. Of course, then there are people arguing the increase is stopped sometimes. This is here for the last decades, but of course, this is clear. When you have a strong eruption, volcano eruption as Pinatubo, you have a decrease here of the temperature increase. If you have El Nino event, then there are peaks. And then in the La Nina events, you have minima in some sense. There is also some not so clear period, but the special years are not so important. It's not a linear process, not a linear system Earth. Therefore, we have to look for the trend, and the trend is very clear. It's increasing. There is no doubt about it. And what is, this is one impact, the global temperature increase. And what are specific effects? What is now? I get here some warning. I hope I can. Okay. One specific effect is the sea level rise. This is also, you have a strong increase during the last decades. And there are several scenarios here you see from 1700s almost constant. But if you calculate scenarios for 2100, this is a rather conservative one, but this shows already 60 centimeter increase. In worst scenarios is already 1 meter and more. And what does it mean? It's not homogeneous because the mass distribution of the Earth is not homogeneous. But let's look for the areas which are most sensitive to this. And this is, as expected, Bangladesh and India, and also Indonesia, where we have already one clear impact because they shifted the capital Jakarta to a new one, to Nusantara, which is in a much more secure area. But also, oops, this was one too much. Also, if we look to US, where most of you are now, I suppose, then you see that the east coast of US is also under big danger to become flooded, and even New York City. As if you see, these are all the areas which could become flooded. This is a conservative scenario, let me say, in about 60 years maximum, and you can imagine which kind of migration would set in. Then this little migration we had in Europe in the last years is nothing against. And this is really a very big danger. One could also look more from a cultural viewpoint, how many World Heritage parts of our culture will be flooded. And you see then there are a lot, for instance, the Botanic Garden in UK, the nice garden in Suzhou in China, and many other places. This is also in US, in Europe, all over the world. It depends on the degrees, but you see that already for 2 degrees, which is realistic, I would say, and is a minimum. And from my viewpoint, there will be a lot of flooding. Of course, then we have extreme events you all know about. You have strong snowfall near the east coast of US. You have wildfires in California. In Europe, we have had heat waves much stronger than before, and one after the other. It's now, it was always called, these are century-like events, but they are now not annual, but very often happening. And this is one important approach, and we should understand the existence and the occurrence of such extreme events. And we try to analyze this via complex system approach, and especially via complex networks. And you all know, I'm sure, that complex networks have origin in social networks as Facebook, where it's very clear what are the nodes, what are the connections in each. Also, we are a little social network now. Some know each other, others not, but due to this combinations, we can spread information, and also opinion formation happens. It's a bit different with the climate. And we try to reconstruct a network from data. And this is also, I was told that several of you are related to data science. This is here really applied data science to reconstruct climate networks. And I started this about a bit more than 10 years ago, 2008, and had a grant where Klaus Hasselmann, now Nobel Prize winner, was in the scientific advisory board, and he listened to me, asked me serious questions about this approach. That time we had not much success, was in the very beginning, but then he thought a while and told me, you should go ahead this way, it has much potential. This was, as you can imagine, very encouraging for me, and what I will present to you now is joint work with several students of mine, which are now in various places, and of course also experts more from the climate side, also from different places. So the first thing is that in contrast to these social networks, the climate is a flow system. Therefore, the network, the corresponding network, is a functional flow network. Functional, why? Because the climate never stops for us to let us have an insight. It's always going ahead. It's dynamic. It's a functional flow network. And how can we go ahead with this? And the idea is the following, that we try to reconstruct a network from such a continuous dynamic system. And this can be understood as some kind of discretization. Also, we are looking whether there is a backbone underlying the climate system as an inverse problem. So how are we doing this? We start with observations. Here are all these observational sites, all these dots. We have time series there, we have temperature, precipitation, wind, humidity, and others. And then we make a causality analysis among the different time series from the different areas, from the different nodes. We consider each of these observational sites as a node. And if there is a statistically significant causality among two such nodes, say here I and K, then we make a connection. That means in the corresponding adjacency matrix, this IK is becoming 1. If it's not significantly, no significant causality, then it remains 0. And if we have such an adjacency matrix, we have the network, and we can also make it weighted. Then we can make it, can apply the network science approaches and techniques. That is the idea. If we apply this to data, then we can immediately infer so-called long-range connections. They are called teleconnections in climate. And this is here for temperature data with more than 100,000 edges. And you see here the strongest connections we found with this causality analysis. And you see these are mostly along the equator and the oceans. And this is, of course, was known. We refound several teleconnections, but we could also specify, say, much more, could follow up their dynamics and also found new ones. And therefore, already this is considered as a very interesting visualization technique in climatology. One can, of course, also make some other projections, as here from polewards, and so to emphasize some other kinds of interactions. So, and if to give you one example, I will, if I have time, I will give you later another example. Was the question, what is the connection between the ENSO, also El Nino Southern Oscillation dynamics in the Pacific Ocean and the continents around to the Indian monsoon system? And we found then several pathways via our network approach and calculated then the most probable with techniques from machine learning, by the way. And it came out that this one is the most probable. That means via the Indonesian archipelago is the strongest connection from Pacific to the Indian subcontinent. And already this was of high interest for climatologists. It looks rather simple, but it's not as simple as it looks like. So now let me go to the extreme events. And here I follow the motto of a very famous physicist, Richard Feynman: test of science is its ability to predict. Very strong. In data science, this is clear, but in physics, this is not so typical motto. It's a really high-level motto. And the question is, can we improve forecasting weather and climate? Why is it necessary? Because all these models, which are now used and refined after all this work by Richardson and so, the global circulation models have a prediction horizon of maximum 2 weeks. And we would like to extend this. Is it possible via our complex network approach? For this, we consider first precipitation, as a very strong precipitation. and try to identify a network among these strong precipitation events. For this, we have to develop a technique because precipitation time series have a lot of zeros. It's often not raining in many places on Earth. And you know, when you have a lot of zeros in a time series, this is horrible. And in order to avoid this problem, we have developed the technique of event synchronization, which is rather simple. You have here two precipitation time series, the region A and B. Then we consider the 10% strongest, all what is above the red line. And the crucial point is now to look whether the maxima of the strongest events happens almost at the same time in both areas. And we have a window, and then you see it's here, and here. And why a window? Why not exactly? Because such precipitation fields have to go via flows from one area to another one. Therefore, we cannot expect to have a strong rainfall in New York and Washington, for instance, exactly at the same time. It needs a little shift, and this is included via this windows of a few days, plus minus a few days. So this is an idea, and if this is not only a few times happened, this coincidence, this synchronization of strong events, then we make again a connection between area A and B. That means, as you see here, we have measures from area I and J. Then we make this synchronization analysis. If this happens, this synchronized behavior significantly often, then we make again a one among I and J and construct so the adjacency matrix. Maybe it's interesting to emphasize that in principle, this approach was already invented 10 years before we did it in neuroscience, because in neuroscience you have exactly the same problem, but here is of course the spiking and activity of brain. Here we are interested in very strong rainfall events. And then of course we have a network and can use the network measures. So now let me give results, application. And this first we are looking for the global pattern of strong rainfall teleconnections. For this we have satellite data, which is very good because we have a good resolution. We have continuous data. Also here we have daily data. And the problem is, of course, that they are not too long because the satellites are not too long ago working. But here we have almost 20 years, which is not bad for our purpose. And then to find or to construct a network of these strongest events, we have to make about 10 to 11 comparisons via this event synchronization. This is not the problem, as you know, for computers, but the real problem is a classic statistical one, the multiple comparison or multiple testing problem. Because we take one node I, and then we compare the data of this node I with all the others. And we use again the data from node I again and again and again to compare with all the others. And this is a multiple testing problem. And due to this, you can get artifacts. You can get results that some areas are significantly connected, although they are not. This is a typical artifact, and one has to make a correction. There are classic corrections as Bonferroni correction or so, but they are too conservative. We tried them first, but if we try them, then it's almost nothing remains. And therefore, the main work on this paper, which was, by the way, the first paper in Nature on climate networks at all, was to find a significance test, to test for a real network, to reconstruct really a real significant network. And here we are looking for significant bundles or coherent spatial patterns. Because this rainfall cannot jump from A to B, it has to go there via some flows. And this is the idea, and this is in some sense also a conditional connectivity, which is already known in statistics, but this is here really especially developed for the climate system. And the result is then, if we consider now Himalaya, this is this red area and some area around North Pakistan, North India, and all the connectivity of strongest rainfall events from this area to all the other areas, then we find a lot of connections. This is here the uncorrected. Here is the corrected, and you see is much sparse, and even the shadow things we should neglect because they are not significant enough. We have higher ambitions, and therefore we have really now a rather sparse network. So now let's look what are typical properties. And for this, we looked for some scaling. That means we calculated how many connections you can have for a certain distance of strong rainfall events, among strong rainfall events. And this is in a log-log plot. Here is a distance, here is a probability or a probability distribution function. And you see here in this area a linear decrease as expected, less connected events if the distances become larger. But then, a bit surprisingly, we have an increase again at about 2,500 kilometers. This was a bit, we wondered, why does it happen? But then if you think a while, then it becomes clear, because this is here, these interactions are due to regional weather systems where thermodynamics plays the most important role, whereas here the teleconnections, the long-range connections, circulation dynamics, Rossby waves, and so plays an important role, and therefore we have an increase, not as much coming back to this original, but nevertheless a significant increase. That means the teleconnections plays really a strong role in the formation, in the global formation of extreme precipitation events. This was really unknown. We also looked then for further details, and we found, for instance, the so-called Silk Road pattern. That means there is a pattern of going of extreme events from Europe till Eastern Asia, till China. Therefore, it's called Silk Road. This was known for high latitude dynamics in the atmosphere via the Rossby waves, but now we find it also on Earth with precipitation events. And this is a strong indication, this is really a new finding, that Rossby waves modulate in some sense such occurrence of large-scale, large precipitation patterns. And this, among this scaling we found, this really opens new ways for a prediction of extreme rainfall events. Let me give one example. This is Indian monsoon, which is very important, and especially is important for the whole Indian subcontinent, and especially important is to forecast the onset of Indian monsoon as early as possible. And the main problem is when to bring out the seed. This farmer brought it out too early. He lost all because all died out. It was dry. If you bring it too late, then the monsoon comes, washes out all the plants because there are no roots developed. And you really have to find a good timing before the onset. And we applied there also our approach via complex networks. We have here ground-based data, Aphrodite, but also our satellite data, and use also classic data. These are precipitation data. And then we used 3 steps. First is the event synchronization complex network approach. This was not enough, but with this approach, we found out the 2 most sensitive regions for the onset of Indian summer monsoon. Then we considered the so-called pre-bifurcation and enhancement of fluctuations. That means when you are coming close to a bifurcation or to a tipping or whatever, which word you would like to use, then the noise, which is always in a system or added to a system, becomes amplified. This is also a typical nonlinear behavior and is used as a precursor of extreme events. And then we also use some special climate conditions there in India and North Pakistan. And when we put all these three steps together, we could indeed extend substantially the prediction horizon. We can now predict the onset of Indian summer monsoon 40 days before the onset, which is much more than it was with classic, with techniques, with available techniques. And this was what we checked with hindcast, also in the past, a success rate of 74%, which is not so bad in climatology. But to show it a bit more in detail, the two sensitive areas we found are North Pakistan and the Eastern Ghats. And this was also a surprise because so far Kerala was considered as the most sensitive area here because onset is here. But the changes, the internal changes in the whole climate system of the whole area is much more dominant in these two areas. That means they are much more sensitive. And here you see that we can have some early warning. If you consider the change of the fluctuations of the variance over all India, you see no effect. But in North Pakistan and the Eastern Ghats, you see really a strong increase of the variations before the onset, and this gives us then the way to make a prediction. And what is maybe interesting, that we were successful with real-time predictions afterwards. We published this in 2016 and could make now several real-time forecasts, and they were all successful. Maybe we do not know, because 74% means we should fail, and we will fail in future at some time. Maybe the statistic is so good due to a global change that things are becoming a bit more simple in some case, a bit more ordered, but this is unknown. But a strong drawback is that we cannot forecast the intensity of the monsoon. And you know, there were very strong monsoons with strong floodings in the last years. And also it would be interesting to include it in operational forecast. This is now under work with Indian institutes, especially for tropical meteorology. We have not only applied this to this Indian case, also to extreme rainfall in Bolivia, tropical cyclones in the Pacific, in the Indian Ocean, especially to extreme rainfall and typhoons and landslides in Japan, El Nino, Indian Ocean Dipole, and are working on further. Only to show that what I showed you so far was rather long time, but for instance, such tropical cyclones, which cause a lot of extreme events, are very short-lived, only 3 till 10 days. And how can we construct it? Which parameters could be useful? And we use then a sliding window analysis for constructing evolving networks. And here the local clustering coefficient is a very useful tool for following up these cyclones. And we could do it really rather successfully in several ways. And this could be also open a very important point for further research of extreme events happening there in the tropics. But let me come at the last point to another very important field of research. These are so-called tipping elements, which are one of the most crucial dangers these days due to climate change. Tipping elements are, as the Atlantic Ocean or El Nino, of course, the poles, also Indian summer monsoon. These are phenomena or area which have the strong possibility, the strong option of showing a qualitative change, of really a rapid change in the behavior. For instance, in the Atlantic Ocean, we have this flow of warm water from Gulf of Mexico and from the south northwards, which makes our winters rather mild in Northern Europe compared to Canada at the same area. And then the cold is going down. And the question is now of these tipping elements, and you can imagine when it's tipping, for instance, melting of the poles of the ice would really have a strong impact on our climate. Therefore, the understanding of tipping points, of tipping areas is very important. Another very important point are the interaction of different tipping points. Is there a cascading or will it remain isolated, regionally, if you wish? And of course, forecasting of tipping. How close are we to a tipping? This would be very important to know and to estimate. And there are several attempts, of course, to study the interactions. You see here some interactions also under which increase of temperature we can expect which tipping at some time, maybe shortly after this increase. The coral reefs are very the most probable tipping element, which is almost done, which is irreversible probably, but also some others. And you see here there are some information about the interactions. And this would be very important to find out. These are here based on scenarios, also on several, on comparing several models for future scenarios of climate evolution. We used in a very recent study, is now in press in Nature Climate Change, temperature data from the last 20 years, from the last 40 years, and studied especially the role of Amazon rainforest area. The role of this is also a tipping point, of course, Amazon rainforest, it could be tipped into savanna, into a dry regime of climate, and this would be terrible. But the question is, which areas, which other tipping points are mainly influenced? And we use then this network approach. And what we found mainly are these red things, and here is a Amazon, there is a strong interaction on the Tibetan plateau and the other also on the West Antarctic ice sheet. This was not known so far. This is really a new result. And we looked at how could this go from here to here? This is a scheme. But we looked then, and this is the advantage of network analysis, for the pathway. How could go the flow from here to here? And this is then the most probable pathway here via the southern Atlantic Ocean, then north to Africa, and then east to the Indian to the Tibetan plateau. And one could also, this is a finding, a data analysis finding, but you have to interpret this, and one can indeed find typical motions of the atmosphere which could be responsible for these three parts, from here to here, northwards and then eastwards. And we really could identify three main typical features in our climate system, rather large-scale features, which could be responsible for this kind of motion. So now I think I should come to the end of my talk, to the summary. I hope I could convince you that climate as well as complex system science are part of physics, and both need interdisciplinary approaches. Here I only gave chemistry, geomorphology, but of course we need physics, we need computer science, and several others. And also it's rather clear that climate is a highly complex system. Therefore, complex system science is a real tool, the real approach to study such a system. What we found is that complex climate networks are really a promising approach. It's not the only one, of course, there are many others, but for several questions, it's really a crucial step, especially to analyze extreme events, the propagation, the understanding of the occurrence of extreme events, and also to get, in some cases, improved predictions as Indian Summer Monsoon, Eastern Central Andes, El Nino, etc. And we hope that this can be also included in operational forecasting systems. But this is all rather in the beginning. I would say even in its infancy. There are many open problems. This approach has, of course, potential for studying other extreme events and maybe even longer forecasts. Then we have to go, so far I only talked about one component, as here's the temperature of precipitation. But climate is much more complex, and we have to include different components from the atmosphere in a multi-layer network. But not only atmosphere, we also have to consider land use, of course, mega cities, for instance, and several other components. And at the end, even socioeconomics. But this all becomes more and more difficult. If you could include these things, would be already fine, I would say. And of course, a very important point is we are working on this. We are not experts, but we collaborate with experts to combine this approach with modern methods from machine learning, because we think one can strongly improve several of these necessary calculations and make it much more operational than due to this. I do not think that one can solve the whole problem via machine learning. I'm a fan of using expert knowledge, and I think with climate networks, one is closer to the real reality, but I'm sure that one can really improve strongly these climate networks via machine learning techniques. And finally, I give you our papers, and with this, I would like to finish, and I would be happy to get questions. Thank you very much.
Thank you.
Thank you. That was so wonderful. Thank you so much. I really enjoyed getting that high-level perspective on so many different issues related to climate change. You so clearly described these very complex issues and taught us all so much. So thank you so much. And we can take some questions from the audience if anyone wants to go ahead. You can just, I guess people can just, I see Mauricio has his hand raised. Mau, do you want to go ahead and ask a question?
Do I? Okay.
Oh, yeah, you have your hand raised. Yeah.
So from my point of view, it's very clear how you construct the network. But then how do you build a model on the network? Meaning, from the network, we can tell which part is functionally connected to which other part. But then, how do we make predictions on it? Very simple, like in a few words, how do you do the prediction once you have the network?
Now, this is the prediction is here also doing via data analysis. It's without modeling. It's only data-based. Also that means we learned from the past, and and then we predicted, as I showed. Let me make this maybe. Clear here for the Indian monsoon. Also first we found out these sensitive areas.
The topology.
Yeah, the network topology. That's right. From the network topology, we found out them, and then we considered the variance of fluctuations of the time series.
Okay.
And this is then we consider, we learned it from the past, and then we look what is the indication for such an increase. And if we see a strong indication, then we can make the prediction.
Okay. Okay.
But of course, you are completely right. This is only the first step. One needs then real models. Also what we have done already is to compare predictions with our network approach with the pure model predictions. What is done in also for a bit longer time in the climate centers in Reading and in Boulder and so. And this was very interesting because we constructed networks from their model data and also from their predictions and compared it with reality, and then we found really differences. Also some problems they have which they do not include in their models. This we could identify in a close collaboration with them. And that means they have to improve the models. This is one way, but in this way, we could also use the models after network reconstruction for real predictions. This is one way, but these are high dimensional models, as you can imagine. The other way is, especially for such tipping areas, to have conceptual models for the dynamics of each of these tipping areas. Say for the Atlantic, for the El Nino, and you have some rather not low dimensional but intermediate dimensional models, and with them you could use indeed predictions, and we would like to have then these conceptual models use the connectivity found by our network approach and then make predictions. That is the other way. This is conceptual. But this is with conceptual, of course, you can mimic only some part of the whole system, and hopefully the most important part for some extreme events also. Also this is another direction to develop further conceptual models and combine them with our network structures. But there is no there is no simple direct way to go to models from this approach, let me say. Of course, you can have formal models, this neural network also, but this is, I think you do not mean this kind of models.
Great, so thank you so much. And then Dr. Neal also has a question.
Yeah, thank you so much for a really fascinating talk. I'm wondering if you could speak a bit on the main challenges for causal structure learning when you have climate data. Like what is it that makes, like a standard PC algorithm or something like that not work, and what do you do about it?
Yeah, this of course people have done in I think from the 80s or so, all these PCA approaches were successful in some sense, but this is, as you know, is a linear.
Sorry, I meant PC for causal structure learning, not PCA for dimensionality reduction.
So, okay, okay. And you mean this? Why do we need causal connectivity, or what is it?
No, my question is, I think you had mentioned in one of your papers that kind of a typical way of learning causal structure, something called the PC algorithm, isn't really sufficient for this kind of data. And so I guess I'm wondering, like, what makes this data so hard, and what do you do about it?
Yeah, then I have it. Thank you. The problem is the dimensionality. It's so high dimensional, the thing. And what we have done was, in one way, was a combination of, by the way, PCA, this to identify the main components in the classic way. And this was then, I think we had then 60 or something like this main components. And then we made a causality analysis among these 60 components. So we have a strong reduction. and this was what I showed in one example when we looked for this Pacific ENSO to Indian monsoon. The first step was then reducing this dimension. And this is one area, but maybe there are also more intelligent ways of dimension reduction, and also more nonlinear ways, because this is a very nonlinear system, as we all know, and that we can replace PCA by some others, and this could be via machine learning, I suppose. I'm not expert enough, but I have a strong hope that this works. And we have also discussions now, first discussions with people from Google. What is this company, this sub-Google company for machine learning? They are very interested in this problem, and maybe we can come with them, but also with other people. We are very open to find other more intelligent ways of dimension reduction. This is the main problem, dimension reduction.
Great, thank you very much.
And also, only to add, this is the system is very dynamic. Also, you cannot expect a stationary behavior, especially due to climate change. We have non-stationary, and we have to cut the times in rather short pieces of times, and this makes the analysis even harder.
Thank you so much. I have a question. So like I remember at one point you showed, you know, like for instance, you were surprised to see something in the Amazon rainforest affecting some very cold region, and you showed them like a kind of a path going through the water, or perhaps this one. And I'm just curious. So then that's based on probably some other physical models of the oceans and the air. And I'm wondering if something like that, can you then place some kind of sensors in the ocean or in those regions, or is it just impossible to collect data in those regions?
No, this is there's a bit. This scheme suggests that it's going via the water. You are completely right. Via the ocean. This is not true. It's in the atmosphere. The processes are in the atmosphere, and therefore it's then easier to understand. But of course, there is a strong coupling between ocean and atmosphere, and ocean circulation plays an important role, of course, in this large-scale motion in the atmosphere as well. And the problem is the data in the atmosphere are now rather good, I would say, due to the satellites. We have very good data, and not so long, but they are really very good, high resolution, and also different heights and so on. But in the ocean, you can imagine we have not very good data. And they start now, for instance, this problem in the Atlantic Ocean. A big question is this conveyor belt, what I mentioned, going upwards, warm water, and downwards, the cold water. Is it still ongoing with the same speed? One has to have measurements, and there is now a big program to install buoys to go it also in the depths, in some depths, but this is only very shortly, a very few years or so. And this is in the beginning. This is a big lack of data. This is exactly the point. And this is always, you have here all the problems, maybe similar also to neuroscience. Nothing is stationary, and we often have a big lack of data. We would like to have much more. It's coming, but one point is then to reconstruct, to learn climate from the past due to other sources, from the very past, from sediments, from sea sediments, from tree rings, and also from stalagmites. And so, as this helps. But to have direct measurements would be much better, of course. These are so-called proxies, indirect measurements. And this is also one puzzle. Therefore, I think climatology was one of the first to develop strongly all these data assimilation or machine learning techniques. They started already in the maybe late 80s or so with this, because there was always a need to combine different data, to complete incomplete data, etc.
It's fascinating. Well, thank you so much. I guess we're at the end of the hour, so I think we will conclude here. Thank you so much, Dr. Kurtz. This was really fascinating and eye-opening, and we really appreciated you coming. Thank you.
Thank you very much.
All right. Well, I'll take care then. Thank you so much.
Thank you.
All right. Bye-bye.
Bye. Bye.